So again, good afternoon, everybody, and welcome to today's BIOCTANE webinar. I have the honor and pleasure to welcome all of you to today's topic, which is about catalysts to convert acetoin and alcohols into jet fuel. So you might remember we had a webinar earlier on about the conversion of acetoin and alcohols towards jet fuel themselves. So now it's more about the catalysts which will enable those processes. And I'm extremely happy that Patricia Pizarro as well as Gabriel Morales will join us today. Patricia is a full professor in chemical engineering at Rey Juan Carlos University and a senior associate researcher at IMDEA Energy. And Gabriel is a full professor in chemical engineering at Rey Juan Carlos University. So they both come from the same university in Madrid. And I'm really looking forward towards their presentation. They mentioned it's going to be an interactive one. So enjoy.
Okay, thank you. Good afternoon to everybody. Let me just some seconds in order to share the screen. Let's give me 2 more seconds. And I had to change the presentation mode. I hope that now you can see correctly the presentation. Just please confirm. Gunnar,
Yes.
it's okay?
Yes, we can. Thank you.
Okay, so welcome to this webinar. It's going to be, as Gunnar mentioned before, is going to be given by Professor Gabriel Morales and by myself. We are going to change from time to time the speaker in order to try not to bother you with the presentation. This time we are going to talk about the catalysts that we can employ or must be employed in the different routes for the conversion of platform molecules into jet fuels. This is the introduction that we are going to cover during the talk. First, I would like to make a short or some introduction about the heterogeneous catalyst. So you can see that this time in this webinar is going to be a more didactic approach. Then Gabriel is going to talk about how can we make jet fuel from residual biomass. Sorry, just a moment. And then he will continue talking about how to use platform molecules in order to be coupled by carbon to carbon coupling using different catalysts. And finally, I will talk about the use of alcohols as feedstocks in order to get jet fuels. But in the particular case of butanediol, which is the platform molecule that we are going to use in this project. So, starting with the introduction, let me to remember you, because I suppose that almost all of you know what is a catalyst, but in general, we can say that a catalyst is any kind of substance that is going to alter the reaction rate without participating directly in the reaction, I mean, without suffering changes in itself. So it is supposed that the catalyst is not consumed and remains unchanged. But in the reality, in many cases, this is not true because they are often deactivated. What are the advantages of using catalysts? Of course, they increase or they speed up the reactions, but we want specific reactions to be speeded up, of course. So if this is true, we are able to speed up the reaction that we are targeting, then we also improve the selectivity of the chemical reaction towards the products that we are looking for. And some important advantages also is that they allow to operate in less drastic conditions. That means normally at lower temperatures and pressures, and this means also to work or to reduce the energy consumption and to improve the process economics. Take into account that in the case of the heterogeneous catalysis, which is the kind of catalysis that we are applying, both Gabriel Morales and myself in BIOCTANE project, involves that it is an interfacial phenomenon. I mean, the reactants, the reagents that must be converted, first has to be chemisorphed on the surface of the catalyst in order to generate some kind of complexes that induce or promote the reaction. So the surface of the catalyst, the properties in the surface of the catalyst are going to play a key role in the activity of these materials. And when I mention properties of the catalyst, I include both types, chemical and physical properties. Both of them are going to be very important. But first, before talking about the properties of the catalyst, what are the main components in a heterogeneous catalyst? Of course, the active phase is the main component of the catalyst. Sometimes it's the unique a component on the catalyst because it determines the interaction of the species and accelerates the reaction. In the case that there is a composite catalyst, involving different components, the active phase is going to be localized in specific areas of the catalyst, both in the external and internal surfaces. The activity of this active phase depends on the kind of active phase, of course, and is determined by different kind of factors, including geometric and electronic factors. Sometimes the activity is because there are some defects, for example, on the active phase that induce this activity. Sometimes it's because the material is a semiconductor. One example here is photocatalysis. The photocatalysts are semiconductor materials and so on. This table shows you examples of different kind of active phases that can be employed with examples of these different kind of active phases and the different reactions that they may promote. For example, metals such as iron, nickel, cobalt can promote hydrogenation or dehydrogenation reactions. Zeolites are very well known as catalysts for cracking, isomerization, alkylation, aromatization reactions. They are widely employed in petrochemistry and refinery processes. But there are other kinds, such as sulfides and phosphides of nickel, cobalt, which also can be used in hydrogenation or hydrotreatment processes. Other kind of components that we can find in a heterogeneous catalyst is the promoters. We can find these kind of components or not in a catalyst. In case we use a promoter, is because we want to improve some properties of the catalyst, and they are normally added in small amounts. Just to give you an example of what can be a promoter can be, for example, a metal or another element that we add into the catalyst in order to avoid the generation of coke on the surface of the catalyst, because the coke can deactivate the active phase. Or even the promoter can induce the elimination of the coke. They can avoid the formation, or they can promote the elimination of the coke by combustion, for example. Also, there can be some inhibitors in the, we can add these inhibitors into the catalyst. In the case, if we add an inhibitor, is because we aim to reduce the reaction rate or to avoid some unwanted reaction. Again, for example, the formation of coke, or in the case, to give you some examples, in the case of alkenes with the triple bonds, if we want to perform selective hydrogenation into alkenes, just to keep a double bond, we can add inhibitors in the metal, which is the active phase of the catalyst, in order to stop the hydrogenation, the saturation of this triple bond, to stop into the double bond and avoid the formation of alkanes. Just to show you, to give you some examples. It's very often that also in a catalyst there is a support. The role of the support is quite important. There are several roles. For example, it facilitates the dispersion and stability of the active phase in order to keep a good dispersion of the active phase on the surface of the support, and then to keep a high accessibility to the reagents towards these active phases. Normally they are porous because then we increase the surface area of the catalyst due to this porosity. It's also quite usually used often that the support has some catalytic activity. It's the case, for example, of the zeolites, that they can be used as active phases and also as supports with catalytic activity. And not always the support exists. Sometimes we have what we call bulk catalyst, which is only the active phase. Different kinds of supports can be employed. Here you have some examples that they are very different in compositions and surface area. For example, silicon carbide with very low surface area, and it's normally an inert support without activity. But in the case of zeolites, they have higher surface area, but also they have activity. And in the case of activated carbons, again, they have very high surface areas, and in many cases also they exhibit catalytic activity. So you have to be careful and to choose carefully the support because in many cases they can have this catalytic activity that can be beneficial or not to your reaction. In the case that we want to shape and to pelletize, to make pellets from the catalyst, this is normally used when we are scaling up the catalytic process and we want to test the catalyst at bench or pilot plant scales. Then we have to shape the catalyst, and here normally we use a binder, which is a material that is going to allow to get this macroscopic shape of the catalyst. But this binder has to fulfill some requirements. For example, it has to provide mechanical resistance to the catalyst against compression or against abrasions, because you have to think that in the case of fixed bed reactors, if we place several kilos of catalyst, in the bottom part of the catalyst is going to suffer a lot of pressure, and then it needs to be mechanical resistance. And in the case of fluidized bed reactors, there is abrasion that can provoke that the particles of the catalyst are broken, and then the binder has to supply this strength, this mechanical resistance. The materials that can be employed here are, for example, clays, which are good in order to provide plasticity to the catalyst, and other kind of supports that have to provide a compression resistance, and also that they have to be stable against chemical attacks. This is, as you can see here in this slide, this will be a representation or scheme of the final catalyst with the binder in macroscopic shape. In this photograph, you can see different shapes and sizes of a real catalyst after this shaping, cylinders, well, a lot of morphologies. But these are in the sizes of centimeters, millimeters, and inside these big particles, you will find different elements, the different components that I told you about. So if you are going in more details and going in depth into the composition of the catalyst, at the end, in the microscopic or nano scale, you will find a material with, for example, a support with pores, as this one here. This is a mesostructure material with very well-ordered pores. And inside, we can include the active phases. This is another picture of another different material with the active phases here, these darker particles that are supported on another material. What about the properties of the catalyst? What are the properties that a catalyst must have? Two types of properties, chemical properties and physical properties. Starting with the chemical properties, they are provided by the composition and the structure of the catalyst, of course, because it depends if it's an amorphous silica material, or it is an oxide, or it can be, we can use a zeolite, as I mentioned before. So depending on the chemical composition and the structure of the catalyst, this material will have different acid-base properties, Also, the concentration of the active sites will be different. It is also very important, the chemical composition on the hydrophilic and hydrophobic properties of the material, and also it can have redox properties. This you can see here in this picture some examples regarding the properties, chemical properties of catalysts. Bronsted acid sites are shown here. These are protons that can be exchanged, and they are very active in many reactions, for example, in cracking or oligomerization, isomerization reactions. It is not only important the presence of this kind of active phases, but also the density. This is the example here. Here there is a comparison of two materials with different concentration of acid sites, what we call surface density acid sites. And sometimes the larger amount of active phases does not mean better activity, because you have to take into account that if the active phases are very close, the acid sites are very close, as here in the second option, the molecules that have to interact and be converted onto the surface of these acid sites becomes very close each other, and then there can be some hindrance problems or contact between them, some interactions that can reduce the activity and the effectivity of the catalyst. So not always higher concentration of active phases means higher activity. Also take this into account. And regarding the hydrophobicity and hydrophilicity of the surface of the catalyst, this is very important, as you can see here, because it's going to determine the affinity with the reagents and with the products. And this is very important because what I mentioned before is that for a catalytic reaction to take place, first there must be an interaction, an absorption, chemisorption of the reagents with the active sites. And then they have to be, the affinity is necessary. But then the product that is created, is generated, must be dissolved and released. And here the interaction with the active site must be lower, of course. Regarding the physical properties, the main physical properties of a catalyst that will affect the activity are those that I show here: the particle size, surface area, pore diameters, and these are some examples of how these properties affect to the activity of the catalyst. For example, as you can see here, there is a comparison of different particle sizes. The smaller the particle size, or the smaller the crystal size of the catalyst, the larger is the ratio between the surface and the volume of this catalyst. And this means higher accessibility to the active sites and higher activity. So normally, lower or smaller crystal sizes is better in terms of the activity. Also, the pore diameter is very important because it can affect the selectivity in the reaction. There may be selectivity to the reagents. This is a comparison of two molecules with different structures. And for example, in this case, in the branched molecule, this molecule could not enter into these pores, and then it could not react. And then we had reactant selectivity. Also with the products, because if the pores are not big enough, some kind of products cannot be created, and then we can achieve a product selectivity. Also in terms of the transition states that must be formed before the product is generated. So these are the different kinds of selectivity that we can get in a catalyst, and this is determined by the pore diameter and pore geometry and shape of the catalyst. So this is very, very important. And now we are going to change to Gabriel. So let me stop sharing the screen. Gabriel?
Okay, thank you, Patricia. It's my time. I'm going to share the screen. Okay. I think you all see the screen already.
No.
No?
Yes.
Yes? Okay.
Yes.
so I can start. Well, after this presentation of heterogeneous solid catalyst from Patricia, now we are moving to the application of this kind of catalyst to the specific field of the project, which is the BIOCTANE project, which is the production of jet fuel from residual biomass, which is the second part of the talk. So first we need to know what is our target. What do we want to produce in this project with the catalyst? And it's just something similar to the jet fuel currently used in aviation sector, which, as you probably know.
Just a moment, sorry, because
Yeah.
in my case it's stop. I don't know, Gunnar, can you see the presentation?
No, I also don't have a picture. Maybe if you try share screen again or stop screen sharing and redo it. Yeah, that looks good. There it is.
No, it's okay.
Thank you, Gabriel.
Now, okay, sorry. I was talking. Well, this is the beginning, so we can start again. Sorry for that. So we're here. How can we make jet fuel from residual biomass? And I was talking just that we have to know first what is our target molecule to produce, which is just jet fuel. Something similar to the fossil fuel, the kerosene that is currently being used in aviation sector. And this fuel, as you probably know, they are hydrocarbons, just hydrogen and carbon, no oxygen, for example. The chain must be in length about from 9 to 14 carbon atoms, and they are mostly alkanes, linear cyclo or isoalkanes, but we have also some part of, well, up to 20% of aromatics in the combination. So how can we perform the transformation to obtain something similar? This is where the subs enter, the sustainable aviation fuels, which should be something compatible with the current infrastructures, compatible with the aviation airplane engines, and also with the storage facilities, but with different origin. They cannot come from fossil fuel. They have to come from biomass, lipid biomass, fats, oil, greases, and so on. Starchy biomass, lignocellulose, municipal solid waste with organic origin also, and they can be also with synthetic fuels coming from the combination of carbon dioxide and hydrogen, green hydrogen in this case, to obtain the liquid. And the routes for the production of this kind, I don't know if you are seeing this bar here. Now, the routes for the production of SAF from biomass are very different. We have a lot of alternatives. Starting from lignocellulose, for example, we can go through gasification to obtain a synthesis gas that can be upgraded via Fischer-Tropsch reaction into jet fuel, or we can produce the sugars, and the sugars can be fermented to obtain alcohol, so can be processed via enzymatic or chemical processing to obtain the so-called platform molecules. With further chemical processing can give the fuel, and also the lipids. The lipids are the most similar biomass-derived molecules to that of kerosene or even diesel molecules, so it's the easiest way to obtain jet fuel, but lipids are not the most available of the biomass. We only have to extract the oils, and by something called hydrotreating, we can produce that jet fuel. So if you analyze these different routes, all of them, or most of them, need of the presence of catalysts, and especially of solid catalysts, chemical processing here, mineralization, dehydration, Fischer-Tropsch, hydrotreating, hydrolysis. Most of the transformation needs the use of catalysts. And of course, the catalyst needs to be well designed to perform the transformation. So if we start from the molecules derived from biomass, usually treat biomass through biotechnological approaches like fermentations to obtain alcohols. Ethanol is the most simple alcohol, but here in the BIOCTANE project, we are analyzing the use of this diol, butanediol, and also an intermediate here, which is acetoin. We will talk about this later. And also we can use other molecules, platform molecules coming from the lignocellulose via hydrolysis, like the famous levulinic acid or furfural, or here the 2-methylfuran, which is a molecule coming from furfural via hydrogenation. If you look at these molecules, which can be obtained obviously in dedicated facilities, the so-called biorefineries. The most important biorefineries in the world right now are those producing ethanol by fermentation. But in the future, we are expecting to have many other kind of biorefineries dedicated especially to the production of these compounds, so they can be considered in the future commodities at large scale production. No? But if you look at the molecules, they are short-chain molecules from 2 carbons in ethanol to mostly 5 carbons in furfural levulinic acid, 4 for acetoin and butanediol, and they have oxygen. All of them are oxygenated molecules, and the jet fuel we are going to produce cannot have oxygen. They are also, the presence of oxygen is because they have functional groups like alcohol, carboxylic acid, ketone, aldehydes, that makes them also a very reactive molecule. So we have to transform this into something similar to the fuel. Remember, 9 carbons to 14 carbons, hydrocarbons. So we need to make the change larger. We have to increase from C2, C5 to C10, C12, and we need to remove oxygen. And how can we do that? Chemically, we need a catalyst. It's a difficult mission, but if we design very well the catalyst, we can perform this transformation in an efficient and economic way. Finally, we are getting a fuel, so it cannot be something very expensive in the production. And we are going to analyze now how, in the field, in the context of the project, of BIOCTANE project, how can we make this transformation I was talking about. Starting in my case from the carbonyl-based molecules, like these ones here, as you can see, they are ketones or aldehydes. Here is furfuran, here is levulinic acid, here is acetoin, and other ketones that are usually employed for the production of this kind of jet fuel, like methyl isobutyl ketone, cyclopentanone, or so. Of course, we need to make the transformation, as I told you before. The first reaction step of the first stage in the reaction is extending the carbon chain length to obtain oxygenated intermediates like this, which have from C10 to C14 carbons in the range of the fuel. And how can we do that? There are several approaches in chemistry, but we are looking in the project to the CC coupling reactions via aldol condensation and hydroxyalkylation, HAA. These are just 2 of the possibilities, but they work very well with these carbonyl molecules. And we need catalysts, of course, for performing this reaction, and we are focusing in the use of some of the catalysts that Patricia told us before, zeolites or metalloorganic frameworks like this represented here in this picture. And then, of course, these molecules have a lot of oxygen. We have to remove it. They also have unsaturations, double bonds that need to be removed because if not, we have a problem with the use of the fuel in the engine. And we need, of course, a second reaction step, which is the oxygen removal. In this case, the transformation is called hydrodeoxygenation. That means that we need hydrogen in the process. Obviously, to obtain a perfectly sustainable fuel, a perfect SAF, we will need green hydrogen coming from renewable energy. And actually, this transformation, HDO, hydrodeoxygenation, is a combination of different reactions like hydrogenation, hydrogenolysis, dehydration. All of them focus to introduce hydrogen in the compounds, in the intermediates, and remove the oxygen. And here, the kind of catalyst needs to be more elaborated. They need to have different active sites and different functionalities, metals to perform the hydrogenation reaction, and also supports with acidity to perform the dehydration reactions. So as you can see here, we have to design a good catalyst to perform these 2 transformations, starting from biomaterial molecules, and the final product, the jet fuel, that we are targeting in the BIOCTANE project. So some examples we are working now or in the past I wanted to share with you is in this case, the condensation of aldol condensation of phosphorus with ketones, this case with methyl-isobutyl ketone, but it could be any other ketone. To obtain this, it could be the intermediate called fume. And a highlighted catalyst here is the use of organic frameworks. This one, based on zirconium, the UIO 66, coming from University of Oslo, is the name. But it's a specific zirconium modified MOF that have adequate balance of acidity in Bronsted and Lewis terms and moderate strengths, which is very important here because phosphorus is very reactive and we need to avoid the presence of strong acidities. Well, the application of this material has limitation, as Patricia told before, because it's very microporous. The pore size is very small for this kind of molecules, and we have tried to modify that. We have tried to modify the catalyst to obtain a better result. So it has limitation in terms of pore size and stability. We propose a modification. We propose a modification of the synthesis conditions to enhance the catalytic activity via introducing a second porosity using modulator during the synthesis. In this case, using hydrochloric acid as modulator during the synthesis, we can produce gaps in the structure here represented, and that kind of gap can be better for the reaction to take place. As a matter of fact, if we try to introduce different amounts of hydrochloric acid during the synthesis, we can see this approximate distribution plot. You can see when the parent material, the MOF without modification, is purely microporous and very small pore size, 6, 7, 8 angstroms in pore size. And when we introduce the different amounts of hydrochloric acid, we are generating a secondary mesoporosity in the range from 14 to 20 angstroms. But it is small, it's still in the microporous range, but it's enough for the reaction to take place. And if we go to the lab and make the reactions, well, that means the modification of the pore distribution means the introduction of missing linkers or missing node defects in the structure, 1 or 2 defects together, and that has a very strong impact on the reaction activity. As you can see here, the parent material and the conditions used in this analysis is almost non-active, no reaction, conversion below 5. But if we go increasing the porosity, the secondary porosity, we can achieve almost 95% activity, conversion of phosphorus and selectivity to the product. So this is a very impressive result coming from the modification of the porosity of a catalyst, as you can see. Another examples we are using with carbon molecules is with levulinic acid as substrate. We can combine it with itself to make self-condensation, obtain this kind of precursors, or with furfural or other furanics to obtain other molecules. You can see all the molecules are similar. They have the right range of carbon chain, but they have a lot of oxygen. This kind of coupling we have performed with zeolites. This will be the dimerization of levulinic acid to obtain different products, C10 products, which are dimers from levulinic acid. And here we have analyzed the use, as you can see in these plots, the use of zeolites beta, with different, the number here means different amount of aluminum, decreasing amount of aluminum from the 12.5 to 180, and other zeolites, SM5 or USY. And of course, the difference between them are the pore structure. They have different pore structure, different shape selectivity, as Patricia told before, and they have also different amount of aluminum. That means that they have different acidity balance in the surface, different Bronsted and Lewis acidity. And here there is an optimum for the H-beta 19. In our case, it's not the highest conversion of levulinic acid, but it's very selective, 100% selective to the products, which is very important in this reaction. We don't want to lose carbon balance, and so we can select the best catalyst. And with this catalyst, we obtained some very good results that were already published a couple of years ago. That in solvent condition, only with the volinic acid now solving the reaction media. With this catalyst, after 24 hours, we can reach roughly 80% of conversion. That means we have a mixture of 80% of these liners with only 20% of the volinic acid and no other products. So it's a very good result. So selecting the proper catalyst, we can improve a lot the results of the reaction. Another example is the condensation of both of these molecules in furfuranolevulinic acid to obtain other interesting materials or precursors. In this case, the zeolite beta is also a very good candidate, but it has too much acidity for the processing of furfuran, which is very reactive. So we have to, in this material, in this beta zeolite, we have to change the activity by reducing the aluminum content and also increasing the Lewis acidity, which is interesting. And we propose it here a modification of this aluminum beta zeolite by reducing the aluminum via the aluminization, extracting the aluminum from the structure, generating vacuums or gaps. With silanose here is a silanose nest, which is very reactive with the zirconium source we are using to introduce the Lewis acidity via zirconium modification. So this is a synthetic strategy where we extract aluminum and incorporate zirconium ideally in this way, as shown here. And we have a material, a zeolite beta, with zirconium and aluminum in the right balance. And again, this modification improves the activity of the material, the performance of the catalyst. This will be the results, especially this the green one, which is the yield to the approach, is very low with the static material without zirconium. But as we increase the amount of zirconium, 2.6% up to 4.0, we see here a clear enhancement of the production of the interesting products. So in this case, modifying the metal we are using as active phase in the catalyst, we can improve the reaction, modify the acidity, and improve the conversion and selectivity. And if we go to the molecule that we are focusing in the BIOCTANE project, which is acetoin, is this one, 4 carbons and 1 keto here, hydroxyl moiety here. Here the reaction is we are using to increase the chains. The cis-coupling reaction is in this case the HAA, hydroxyalkylation. Alkylation is a two-step reaction. First, with 2-methylfuran as secondary substrate. Here is the mechanism of the reaction. We have acetoin, methylfuran. They form an intermediate that can evolve with a second reaction. This first reaction will be the hydroxyalkylation, and the second reaction will be the alkylation. That's why we call it hydroxyalkylation. And then we have the compound B. These compounds are the made for different formulations, C9, C14, and the other one is tolance. So we can aim for those compounds. Here, the catalyst may need to be a strong acid catalyst, like sulfonic acid resins, good acetoin conversion, selectivity to this compound, and very good utilization efficiency of the other compounds. So they work okay. Indeed, we have performed optimization of the reaction conditions in terms of conversion, in terms of selectivity to the compound, and you can reach very good results finally. And those reaction conditions shown in the slide, 90% conversion of the acetoin with 80% selectivity, which is a very good, a very high result. But the point here is we have bad reusability of the catalyst. So we are looking now at how can we change this catalyst, and our proposal is to modify, instead of using a sulfonic resin based on an organic polymer, introducing a support based on silica. We change the support. Using a mesopore support like here, and the sulfonic acid will be anchored, grafted onto the silica. And here, as you can see in this image, underneath with the sulfonic resin, the reusability in 5 uses was bad. We are losing activity, but with this kind of materials, the reusability is very good. They are stable in reaction. So modifying the support, we can get a good result in the stability of the material. And even we can continue with the modification of the silica surface to improve other parameters like hydrophobization. And in the second reaction test, we need to remove the oxygen, the saturation, all the moieties with oxygen, like hydroxyl, carbon, and so on, because we need a fully compatible jet fuel. And actually, the hydrogenation, as I told you before, is a cascade of reactions. It means the hydrogenation, hydrogenation, dehydration, sequential steps. We need multifunctional catalysts able to perform all the reactions in a row and efficiently to minimize losses. So, what are the catalyst requirements in this case? We need metal active sites for the reactions. We need acid sites for the ring opening and dehydration. And we need to optimize the balance between them because it's very critical. And also have some water tolerance because we are removing oxygen in form of water. And also they are going to be performing reactors under high pressure and temperature. So possibilities, we have these molecules, we want to obtain this, we need to provide this kind of catalyst. We need to include metals. Noble metals are the best, most active, but they are expensive, so we can go to non-noble metals like nickel, and different supports with acidity, like isolite, aluminum, sulfate, zirconia, so on. And also not only the composition, but also the synthesis procedure is very important on the catalyst properties. An example here would be the selection of a good metal type with the oxide, activate the surface because we need the reduced form of the metals, analyze if there is any synergistic modification of the supports, analyze the stability, analyze the reducibility of the metals in the catalyst, taking into account the acid site and stability in the reactor. So many parameters to optimize. These reactions are very complicated. We need to have in mind the things at the same time when we make the design of the catalyst. And also the reactions are not easy. This is just a model reaction we are using, starting from a very simple molecule, one oxygen, and to obtain the final hydrocarbon that would be interesting for jet fuel. You can see there are different routes, different intermediates, and the catalysts have an effect on all of them at the same time. So it's something difficult, and this is the real catalyst engineering. This is an example where we need to engineer our catalyst to come from the substrate to the final product in a good yield. An example we are using, for example, is just incorporating nickel with aluminum and niobium in a material, in a catalyst to make this HDO reaction. We need to incorporate different metals. As you can see here, the best catalyst in our case is the combination of niobium and alumina support with nickel as the reducting metal, but with a promoter which is rhenium. If you combine all of them in the perfect way, in the perfect synthesis condition, you can achieve a conversion of 99 with the yield of the same molecule 99 in only 30 minutes. So modifying the catalyst, you can improve the reaction. And finally, in the case of the BIOCTANE project, we are working right now in this molecule, which is acetoin 2-methylfurans with 14 molecule, which is not an easy transformation. As you can see here, starting from this molecule to obtain the final hydrocarbons, we have different routes and different kinds of intermediates, and analyzing the performance of this catalyst combining nickel and rhenium, we have obtained preliminary results achieving the hydrocarbons. We are looking at the C12, C10, these yellow and blue lines here. We expect to increase them in the future, but it's not an easy task. Now moving again back to Patricia.
Yes, I'm going to share the screen again. Just 1 second. It's only 4 more slides, so don't worry, I will finish. Just the only things to be able to activate the presentation. Again, I need to change the configuration. No, shall I Are you watching currently the presentation, or shall I change to?
Currently, it's PowerPoint, so you will have to change.
Okay. So then, oh yeah, I don't know why, because it was supposed to be here. Okay.
I think you have to, yeah.
Yeah, you have to change the configuración de visualización.
Okay.
Yeah.
Now it's okay, no?
Yes,
Now
it is. Thank you.
Perfect. Thank you. So just moving to the last part of the presentation, also in the project BIOCTANE, we aim to convert one alcohol into jet fuel. In particular, is this molecule 2,3-butanediol. So I'm going to talk about this molecule mainly because there are many alcohols. There is a lot of literature about the conversion of different kinds of alcohols, for example, methanol into fuels or jet fuels in particular. The challenge here is that butanediol is a diol molecule with two OH groups, and this is more challenging because we need to completely dehydrate this molecule, getting butenes. Then in a second stage of oligomerization, we convert this butene into larger olefins that finally they are hydrogenated and we get the jet fuels. The idea in the project is to carry out these two first catalytic steps, dehydration and oligomerization, in one reactor. But the challenge here, another challenge, is that both catalytic processes operate at different conditions. The dehydration normally is carried out at lower pressures and higher temperatures than in the case of oligomerization. And of course, the catalyst functionalities are different because in the first case we are looking for dehydration sites, and in the second catalyst we are looking for oligomerization sites. One common point for the two catalysts is that we are interested in catalytic systems with high porosity and surface area in order to have higher accessibility and better dispersion of the active phases. So the strategy that we followed here is first to study in a separate way the dehydration reaction. So we were looking for a catalyst which was able to fully dehydrate this molecule into butenes, and then couple in a second bed, but in the same reactor, a second catalytic bed in order to oligomerize the butenes that we were achieving. Then, in order to maximize the conversion of butanediol into olefins, into butenes, we need the full dehydration of this molecule, which is quite challenging, as I mentioned before. And first, we were looking at literature about different reaction pathways that can lead into the formation of the different butenes. And you can see here that there are different pathways in order to get these products. In all cases, we need acid size. This is one of the things that we need to look for then in a catalyst. We need acid size because they are going to dehydrate, to extract the alcoholic groups in form of water. But if you pay attention in these reaction pathways, normally, we also need hydrogenation steps in order to reach the full dehydration. It's not only with acid size, then we also need some metals, metal active phases that promote or activate the hydrogenation steps in order to reach the final products. In fact, also in addition, in the case, for example, of this first route with acidic size, it is theoretically possible to reach a butadiene just with a direct dehydration, complete dehydration of the molecule, but you will see that this is very difficult in some examples that I will show later. In terms of, I think, is thermodynamic reasons, it's really difficult to reach a full conversion to this molecule in a direct dehydration as is marked here. Also, if we introduce metals with hydrogen in the with metals in the catalyst, there could be dehydrogenation reactions promoting other kind of unwanted products. Pay attention also here, methyl ethyl ketone and methyl propanol. These are two intermediate products that are very difficult to overpass. This is the main barrier in the reactions in order to get the butenes, as you will see later. But in conclusion, we need acid size and metals, also hydrogen in the reactions if we want to get a full conversion into butenes. So the catalyst design includes the selection of the metals, also the method in order to disperse this metal into the support. It is also important the density or concentration of acid size in the catalyst, as I mentioned before, and of course the operation conditions, pressure, temperature, the composition of the gas carrier, if there is or not hydrogen in this gas carrier, is going to be very important. The reaction setup that we have used is this one, just to at least show you the scheme of the reaction system. It's a fixed bed reactor. We place here the catalyst. We feed the butanediol with a HPLC pump. We introduce also the gases in a downflow system. These gases can be only nitrogen or a mixture with hydrogen. And at the bottom, we collect the liquid after condensation of the vapors, and the part of the vapors that are not condensed are collected here and are also analyzed in a micro-GC. Just to give you some examples about the importance of the catalyst design and the composition and the chemical structure and so on, as I mentioned before. First, we tried here in this reaction with this reaction system a zeolite, nano-cetacean 5 zeolite with a silica aluminum ratio of 40, with a moderate acidity at different conditions in nitrogen, at 1 bar of pressure, 10 bars, or in a mixture with hydrogen. And as you can see here, the activity was not good in terms of the production of butenes, because, for example, in the first case, only nitrogen at 1 bar of pressure, the conversion was very low. The yellow bar is butanediol, and then you can see that the conversion was really poor. And in the case of using higher pressures or even hydrogen, we improved the conversion of butanediol, but the main product was methyl ethyl ketone, MEK, as you can see here, which is the intermediate component I told you before that is really difficult to overpass. The production of butenes was observed, but in a very low amount. So just only acidity at different conditions was not enough for this reaction. Then we have poor selectivity to butenes. Then we move to the combination of the acidity of the zeolite with a metal, which normally is used in hydrogenation reactions in order to couple both functionalities, hydrogenation capacity and acidity, according to the mechanisms that I showed you before. In this case, as you can see here, the red line is the conversion of only cetacean 5, including or introducing nickel improves a lot the conversion of the butanediol, but anyway, the conversion was mainly to, again, methyl ethyl ketone with a very small production of butenes. So again, we achieved very poor selectivity to butenes in this case. So nickel was not good in our reaction. Then we move to another method that is used in hydrogenation reaction. In this case, is copper, supported on the same zeolite in order to compare between the different catalysts. And here you can see that there was a very strong change on the activity performance. In the case of the left graph, is the copper onto the zeolite with a silica aluminum ratio of 40, moderate acidity. Then here, the olefins productions, butenes, is the red bar, this one. It was much higher than in the previous reactions, and the MEK production was smaller. So here we were in the good direction, we were getting better results, but it was much better in the second case. Here is the same catalyst, but using a support, the same zeolite, but with lower acidity, with a higher silica aluminum ratio. And then we observe a drastic improvement in the production of olefins with almost no production of methyl ethyl ketone. So we were able to overcome this barrier for the production of this intermediate what was not desired in a project. So it's a way to show you the importance of selecting the metal, the appropriate metal, and the appropriate acidity of the catalyst and a good combination between both functionalities. It's not tricky at all. Moving to the oligomerization step, once we found a very good catalyst able to fully convert butanediol into butenes, now we need to oligomerize these butenes. I'm not going to show you results here because we are working now in this step, but just to show you the importance also again of the functionalities of the catalyst. This reaction of oligomerization can be catalyzed by acidic sites, is the case, for example, of the zeolites, and in particular, a Bronsted acid site. This is a Bronsted acid site on a zeolite, a proton, that is on the structure of these zeolites. So the mechanism normally is like this one. There is an interaction between the Bronsted acid site and the olefin, butenes, ethylenes, any kind of olefin, and a carbanium ion is generating. Then, after this generation of the carbanium ion, other olefins can be included, incorporated, attached into the molecule, and then the oligomerization takes place until there is the termination and the release of the molecule, releasing again, getting free the active site. Anyway, when we are using acidic sites, you have to take into account that site reactions can take place, which are illustrated here. For example, isomerization reactions. This is very typical of reactions promoted by Bronsted acid sites. There are many works in the literature using zeolites for oligomerization. It is a very widely studied topic. And this graph shows you a comparison between different zeolites, the zeolitic structures. These are the zeolitic structure, MTT, NFI. NFI is the structure of cetacean-5 zeolite, the one that we are using. And you can see here in the x-axis the geometric surface area of the pores of the zeolite. It's more or less related with the pore size of the zeolite. So the larger, there is a big impact on the pore size of the zeolite, on the activity, on the kind of products that we can get. For example, what we found here in this graph, I'm going to give you some conclusions, is that when the zeolite has a smaller pore size, there are higher constraints, more restrictions of accessibility of the reagents to the acidic sites that are inside the micropores, and then the products that are generated are mainly linear oligomers. It's oligomerization reactions, but getting linear hydrocarbons. In the case that we are using zeolite with larger micropores, then these hydrocarbons that are generated, the olefins, are more branched. They have more branches because they can be produced inside the pores. And normally, what it has been found, and there is more or less a consensus in this part, is that cetacean-5 zeolite is the one providing the better balance between the pore size and the connectivity of these micropores, and then giving the better productions of hydrocarbons in terms of selectivity. But the oligomerization reaction can be also promoted by metals. For example, nickel is another kind of reaction, is summarized in this part of the graph. This is taken from this publication, and when nickel is catalyzing the oligomerization reaction, it is called two oligomerization pathway. This is the example for ethylene. But if we combine nickel with a zeolite, we support nickel or exchange nickel with the protons of the zeolite, and we prepare a composite of nickel with the zeolite, the acidic size, then we have a combination of all these possible reaction pathways. You can see that now this is not tricky. It's very complex, the different reactions that can take place. There is the oligomerization from nickel, but then the butenes and the larger oligomers that are generated on the nickel parts then move to the acidic sites of the zeolite, and there they can continue oligomerizing, or they can be cracked, they can be isomerized, and so on. So this is very, very complex. Regarding the nickel phase, it is not clear what kind of nickel is the most active in the oligomerization reactions. It is thought that maybe it's nickel 2+, but it's not clear because also depends on the interaction with the support that we are using. So it has to be investigated in any case. Regarding the zeolite, in the case of 2005, also here we have to pay attention on the textural properties and the crystal size. Because, for example, if we are using smaller crystal sizes, the activity is much larger, as I mentioned before, because the radial surface volume is higher. So the activity, the reaction rate is higher. But then there is the counterpart that there is a faster deactivation by coking, because also the oligomerization and polymerization is too fast that coke can be deposited on the external surface of the catalyst and the catalyst can be deactivated. So we had to find the correct balance in this issue. Again, the crystal size, in terms of what is happening inside the catalyst, inside the zeolite. If the zeolite has a very large crystal size, inside the catalyst, inside the crystal, there can be also oligomerization and polymerization reactions that deactivate the internal part of the catalyst, of the crystal. So it is important to shorten the diffusion path length of the catalyst, reducing the size, the crystal size. So again, these two parts seems to be opposite. No, you have to find the balance, because smaller crystal sizes deactivate slower the internal part of the catalyst, but faster the external part. And the reaction rate for the oligomerization is faster. So what is better? You have to try. There is not a key universal rule in this part, and this is what I want to tell you, the main message I would like to send, that you have to investigate and to find the better balance depending on the reaction conditions, the catalyst, the metal that you are using, and the support. For example, it uses a very high aluminum content zeolites with high acidic densities. Also, it has been found that it is promoted the coking and then the activation of the catalyst. For the BIOCTANE project, we are investigating. We will focus on a metal supported on the zeolite, CEST, but we need to find this balance as I explained you. Of course, in addition, we need to match this catalyst to the catalyst for the dehydration, because they have to work in the same reactor. So we have to find a catalyst which is able to operate for the oligomerization, but in the conditions of the dehydration. So this is quite challenging, and this is something we are working now. And this is everything from our side. These are maybe the 3 main conclusions, but there are much more conclusions that we have been mentioning and telling you during the talk. So thank you to all of you for paying attention, for being here, and it will be a pleasure for Gabriel and for me to answer any questions you may have. So thank you.
Thank you very much, Patricia. And Gabriel, of course, thank you as well for this deep dive, not only into the BIOCTANE process, but also for the broader picture on catalysts and all the implications that has. It seems to me like a certainly not small, like a large microcosm in the area of process engineering. So there's a lot to discover, and I'm pretty sure that we just got to see the tip of the iceberg. So thank you very much for that. Just emphasizing it once again, if you have any questions, feel free to post them either in the chat or in the Q&A function, which should be on the lower side of your screen. And in case someone is just typing, I'll leave you with a few organizational notes at this point. If you would like to receive a participation certificate for this webinar, just send us an email to info@bioctane.eu. If you have any questions regarding the webinar, you can, of course, also use that email address. We will also publish the recording of the webinar in the next few days on our website, and you will also notice on our social media accounts once it's published. And one more item you might want to mark in your calendars is the scientific workshop that the BioCTANE project will host in Madrid, which is going to take place on the 7th of October. So there's still a little bit of time to go until then. And yeah, as long as you follow us, for example, our newsletter on our social media accounts, you'll receive regular updates. One of the most recent ones has been that you can already register for that scientific workshop. On our homepage, there should be a button which says Scientific Workshop Registration, and it should get you easily there, and you'll receive further information rather quickly. Having said that, I don't see any questions in the chat so far, and looking at the time, I would propose to close this webinar for today, unless you have any important other points to mention, Gabriel or Patricia.
No, it's okay. Sorry, because it took a bit longer than expected.
Yeah.
Presentations.
Sorry for that. Sorry for that.
I hope we didn't bore too much the audience.
I don't think so. I don't think so. There was a lot of content. So thank you both very, very much. Maybe just one more item. There will be one more BioCTANE webinar hosted at the beginning of July. So you will also receive an update on that. And having said that, thank you very much, Patricia, Gabriel, and also all of our listeners, so to speak. Have a nice afternoon and looking forward to see you soon. Bye.
Thank you. Bye.
Bye. Thank you, Gunnar. Goodbye.